mechanical properties of crystals include hardness, cleavage, parting, elasticity, tenacity, plasticity, brittleness, and ductility. These properties are detected by mechanical impact on mineral. So, what does it mean to say that one mineral is harder than another? Hardness is the resistance of a mineral to scratching, and it is one of the more useful diagnostic properties. Relative hardness is easy to determine. All you have to do is rub one mineral or substance against the other. The substance that is not scratched is harder. This property reflects the strength of the chemical bonds between atoms, ions, or molecules, which are a part of minerals. The absolute value of hardness is determined by measuring the area of the impression left by a standard diamond pyramid on the crystal face under the vertical load. Then, the hardness value is determined by the presented formula. A relative scale to measure hardness was devised by Austrian mineralogist Friedrich Mohs in 1822 and is the standard scale for measuring hardness. The following chart indicates how you might test a mineral for hardness according to Friedrich Mohs scale. 1 is the softest and 10 is the hardest mineral. To demonstrate how to use the scale, understand the following example. Suppose a mineral scratched gypsum, but not fluoride. Then it has a hardness between 3 and 4. Several common household items have a fixed hardness and can be used to test for hardness. You can see it in this table. Fingernail has a hardness of 2.5, penny 3, knife blade and glass are 5.5, and steel file or streak plate have hardness of 6.5. Cleavage. Cleavage is the ability of minerals to crack or split in certain crystallographic directions with the formation of smooth surfaces. This property entirely depends on the internal structure of minerals and reveals itself in directions with weak cohesion forces between the particles of crystal lattice. Quality of cleavage can be categorized into 5 qualities: perfect, good, poor, indiscernible or indistinct, and none. Minerals with perfect cleavage will cleave without leaving any rough surfaces. The crystal splits into the finest lamellas with a mirror surface, for example, mica, gypsum, and talc. Minerals with good cleavage also leave smooth surfaces, but often leave over minor residual rough surfaces: calcite, halite, fluorite. On mineral with poor cleavage, the smooth crystal edges are not very visible, since the rough surfaces are prevailing: feldspar, hornblende. If a mineral exhibits cleavage, but it is so poor that it is hardly noticeable, it has indiscernible cleavage: apatite. Minerals with no cleavage never exhibit any cleavage. Thus, broken surfaces are fractured and rough. Smooth surfaces are absent: quartz or cassiterite. Cleavage has a close relations with fracture. Fracture is a surface appearance formed as a result of mineral splitting or breaking not along the directions of cleavage. Cleavage and fracture differ in that cleavage is the break of a crystal face where a new face is formed, whereas fracture is the chipping shape of a mineral. Types of fracture are the following: even or smooth fracture that forms a smooth surface. This type is characteristic feature of minerals with perfect and good cleavage. Conchoidal fracture resembles a shell with a smooth, curved surface. Chalcedony, quartz. An example of conchoidal fracture can be seen in broken glass. Uneven. Fracture that leaves a rough or irregular surface. It is typical for minerals with indiscernible cleavage. Opal, nepheline. Huckley fracture resembles broken metal with rough points. Splintery fracture. The surface of a split is covered with elongated splinters. Gypsum, hornblende. And earthy fracture. The surface is matte and rough. Limonite. Some references may describe additional fractures not mentioned above. To test mineral using cleavage and fracture, firstly, you should observe if the specimen has any cleaved surfaces or fractured edges. If it has cleaved surfaces, the quality of the smoothness should be noted. But if there is no evidence of cleavage, the only way to check cleavage is to chip off a piece and observe the fresh mineral surface. Other mechanical properties that are of secondary importance are also used in the identification of minerals. Brittleness is used to identify native sulfur, ductility for native metals, flexibility for chloride, talc, elasticity for mica. Let's talk about chemical properties of minerals. A special property that identifies some halide minerals is water solubility. Water-soluble minerals often have a characteristic taste. For example, halide is salty and sylvite is bitter. To test mineral for taste, you may lick it, but you must be confident that the mineral is known not to be poisonous. Odor. Several minerals give off a distinctive odor in certain conditions. For example, minerals that contain arsenic release a garlic smell if struck or heated. Native arsenic give off a very mild garlic smell in normal room conditions. The reaction with dilute hydrochloric acid is used to identify carbonates. The reaction proceeds according to the scheme given. The reaction intensity differs and allows us to recognize minerals that look alike. Calcite boils up violently. Dolomite boils up only in fine state. Magnesite boils up in fine state if hard hydrochloric acid is used. Siderite. Emission of carbon dioxide doesn't occur. After acid is dried, a yellow stain forms on the surface of the mineral. Consider other properties of minerals. Density or specific gravity of minerals is determined approximately by waving on the arm. Distinguish heavy minerals with density more than 4 grams per cubic centimeter, medium minerals from 2.5 grams per cubic centimeter to 4 grams per cubic centimeter, and light minerals with density less than 2.5 grams per cubic centimeter. The specific gravity depends on the chemical composition of the minerals. In absolute units, the mineral density varies from 0.6 to 22.7 grams per cubic centimeter. Several minerals react when placed within a magnetic field. Some minerals are strongly attracted to a magnet. These minerals are called magnetic: magnetite, pyrrhotite, native iron. Other minerals are not attracted to a simple magnet, but they acquire magnetic properties under the influence of the electric field: biotite, sphalerite, pyrite. These minerals are called weakly magnetic, and the rest part of minerals is non-magnetic. So, summarize the lecture. Minerals are vital compounds of our lives. We use them daily, and the existence of a modern human without minerals is almost impossible. Also, mineral is a term with different meaning. For miners, mineral is anything taken from the ground. But for geologists, mineral is naturally occurring inorganic solid that has a particular crystalline structure and can be represented by a chemical formula. Crystalline structure and chemical properties give minerals unique sets of properties that allow identifying them with sufficient level of accuracy. These properties are called diagnostic and divided into optical, mechanical, chemical, and additional properties. With knowledge of these properties, identification procedure of most common minerals in the Earth crust is unmistakable.